Imagine stretching a taut silk sheet, then lowering a heavy brass orb into its center. Marbles rolled nearby traced gentle spirals toward the dip, compelled not by some hidden chord, but by the sheet's own sagging geometry. Replace silk with spacetime, marbles with planets, and you hold the essence of a geodesic, the straightest path available when straightness itself is curved. Now, follow tiny Mercury, closest of the sun's attendants. For centuries, astronomers logged its orbit, expecting an ellipse that reset perfectly each lap. Yet decade by decade, the planet's closest approach, its perihelion, inched forward. As though Mercury sensed a groove in space no Newtonian map had drawn. Classical perturbations from Venus and Jupiter explained most of the drift. But 43 arc-seconds per century remained untamed, a discrepancy minuscule to the human eye, colossal to the equations. Einstein's fresh mathematics closed the gap overnight. In his tapestry, Mercury is not tugged off course. It obediently follows a geodesic carved by the sun's mass, because space-time near that furnace is more steeply dimpled than Newton ever guessed. The planet's path rotates, slowly, inexorably like a clock's hand turning through cosmic noon. Extend the notion, and every falling raindrop, every drifting Voyager probe, every mote of cosmic dust is simply inertia set free, honoring the contours beneath it. Forces become reminders, nudges that something, a mountain, a rocket thrust, a photon's pressure is urging matter away from the route space-time prefers, the universe. In other words, supplies rails invisible to our senses, yet absolute in their guidance, and motion's deepest instinct is to stay on track. If space-time shapes where things go, it also shapes when events unfold. In 1962, physicists Robert Pound and Glenn Rebka perched a gamma-ray source atop Harvard's 22-meter Jefferson Tower and set a detector at the base. Photons descending the shaft gained a whisper of energy, their wavelengths shortened because, in Einstein's universe, clocks tick faster the lower they sink in a gravitational well. The measurement, precise 2 parts in 100 trillion, proved that time is as pliable as space. 14 years later, atomic clocks boarded commercial jets. After circling the globe eastward and westward, the flying timepieces disagreed with siblings left in the lab. Mere nanoseconds adrift, yet exactly what relativity foretold once one accounted for altitude. Gravitational dilation and speed, special relativistic slowing. Our species had, for the first time, carried pocket-sized proof that time is not universal currency. It earns local interest. Today, an invisible lattice of 30-plus GPS satellites keeps your phone from wandering off cliffs. Each craft orbiting 20,000 kilometers up experiences weaker gravity and higher velocity than ground receivers. Their onboard clocks race ahead by 38 microseconds per day. Enough that, without relativistic correction, Google Maps would misplace you by 10 kilometers after a single sunrise. Engineers pre-offset the tick rate and continually tweak it, allowing geodesics both spatial and temporal to guide aircraft, farmers, and late-night pizza couriers. Thus, gravity is not a force that drags clocks, it is the statement that clocks and rulers alike belong to geometry. Where space-time dips, moments lengthen. Where it stretches, seconds shrink. On this supple stage, inertia means more than moving freely. It means living in a time that is patient or hurried according to the landscape beneath your feet. On the morning of the 29th of May 1919, clouds parted over the island of Principe, just long enough for Arthur Eddington to photograph a total solar eclipse. When the plates were developed, starlight skirting the sun appeared ever so slightly displaced, bent, as if space itself wore a lens. Einstein's telegram to his mother was understated. Predictions confirmed. Yet in that shimmer of deflected photons, 2 great notions fused: inertia's straight line. Loyalty and light's own unwavering speed could coexist only if the line itself curved. A century later, the Hubble Space Telescope delights in cosmic calligraphy. Massive galaxy clusters warp space-time so deeply that distant galaxies behind them smear into Einstein rings and luminous arcs. These natural telescopes magnify objects otherwise too faint for any glass we forge, revealing infant galaxies forming just a few 100 million years after the Big Bang. Map the distorted images carefully, and an invisible scaffold emerges. Dark matter filaments outweighing luminous stars 5-1, yet revealed solely because light refuses to break ranks with geometry. Even solitary stars can act as magnifying glass. When a foreground star drifts across a background one, its minuscule gravity brightens the latter for days. Microlensing. Offering a sensitive scale two-way exoplanets colder than Pluto, no rocket nudges these photons. They coast inertially, tracing null geodesics, whose very definition is set by spacetime's curve. Thus, every twinkle is also a testimony. Whether forming rings around clusters or whispering through solar eclipses, light evidences a truth more lasting than stone. In the universe's court, even massless messengers must obey the contours that matter and energy script upon the cosmic parchment. Geodesics are usually serene, but let two black holes pirouette a whisper apart, and the stage itself begins to quake. Space-time ripples outward at light-speed gravitational waves, lengthening some directions while squeezing others, like a cosmic accordion. For a century, they were mathematics in search of a microphone, until the 14th of September 2015, when LIGO twin interferometers, arms for kilometers long, mirrors polished finer than starlight, heard a transient chirp. The detectors did not budge through space, rather space slid back and forth through them by a width 1/10,000th, that of a proton. A 1.3 billion-year-old black hole merger had plucked the geodesic web, and Earth resonated in reply. 2 years later, another tremor arrived, this time from colliding neutron stars. Observatories worldwide caught the afterglow. Gamma rays, X-rays, even visible kilonova light seconds after LIGO's ping. Geometry had delivered both when and where the crash occurred, proving that space-time's vibrations can guide telescopes as surely as they steer falling apples, closer to home. Gentler geodesic deviation tugs twice daily at Earth's oceans. The moon and sun stretch our planet into a living hourglass. Tides lapping coastlines in rhythmic tribute to curving trajectories. On Jupiter's moon Europa, the same stretch may warm an ocean beneath ice crusts, stirring minerals that could seed alien biology. Whether they rage as black hole arias or murmur as tidal sighs, these deviations remind us that inertia is not a rigid doctrine but a dialogue. Geodesics can flex, twist, and resonate, revealing in their trembling both the hidden violence and delicate harmonies of a universe forever in motion. Imagine two starships, unpowered after launch, drifting a million light-years apart in the vast stillness between galaxies. In a universe ruled only by inertia, their separation would remain unchanged, each vessel charting its own lonely geodesic. Yet observations of distant supernova tell a different tale. Space itself is accelerating, urged outward by an enigmatic pressure we call dark energy. In this ever-swelling arena, mathematicians dub it day-sitter spacetime. Geodesics diverge exponentially, run the cosmic clock forward, and the starships watch each other fade. It's not because engines fire, but because the metric beneath their hulls stretches. Beyond roughly 16 billion light-years today and creeping closer every century, recession speed exceeds light. Beyond that event horizon, no new signal, however urgent, can ever arrive. It is not distance that dims the stars, but geometry rewriting the rules of reach. For tomorrow's interstellar navigators, accounting for that drift is as vital as Newton's gravity was to Apollo. Concepts already germinate. Autonomous craft might triangulate their position against the millisecond heartbeats of pulsars, celestial lighthouses whose rhythm factors in relativistic redshift. Deep space probes could compare laser links to remote atom clocks on Earth, updating course as dark energy expansion leans on every ruler. Even our modest Voyager 1, coasting inertially since 1989, will one day measure its speed against a cosmic background that has slipped beyond its radio whispers. Thus, the fate of motion is written not only in mass, but in the vacuum's own inscrutable script. Straight lines will forever exist, yet the canvas they cross is inflating beneath their feet, promising a solitude grander and stranger than any gravity-bound poet ever dreamed. We have followed inertia from the silk sheet swirl of Mercury to the tremor of space-time itself, and everywhere the message echoes: motion is geometry made manifest. Freefall is loyalty to curvature. Time dilation, lensing arcs, and gravitational waves are footnotes in its flowing prose. But geometry, we now see, is not static parchment. Dark energy is quietly redrafting the grid, pushing galaxies beyond view, stretching every meter of emptiness into something more expansive than before. Where does this silent pressure come from? Is it Einstein's cosmological constant? Vacuum energy with a density that never dilutes? Or a dynamical field? Quintessence, evolving like a slow tide beneath the stars? How can nothingness possess heft? And why does its influence grow just as starlight culture arrives to notice? These riddles tug at the frontier of both observation and theory, challenging particle physics, quantum gravity, and our deepest intuitions about what a law should feel like. In the next part, Dark Energy's Silent Push, we will chase the evidence. Type Ia supernova yardsticks. Baryon acoustic ripples frozen in galaxy swarms. The subtle imprint on the cosmic microwave backgrounds, coldest hollows. We will weigh rival models, ride future telescopes like Euclid and the Vera Rubin Observatory, and glimpse how the universe's ultimate trajectory. Endless stretch, big rip, or gentle thaw, depends on the character of this most invisible actor. So steady your imagination. The stage itself is moving, and to understand motion, we must now interview the stage. An empty theater whose very planks are swelling beneath the spotlight of our curiosity.